Hello everyone, welcome to lesson number 30. Today we are going to continue what we were starting yesterday with section 3.1, but today we are going to extend it and start looking at relative extrema. So let's start with a quick review of what we were going over in lesson 29, which were our guidelines for finding intervals on which a function is increasing or decreasing. So the three steps you're going to do are to first locate your critical numbers, and remember critical numbers happen anywhere where you have that horizontal tangent, so where your derivative is equal to 0, or also at your vertical asymptotes, vertical tangents, and cusps. So once you locate your critical numbers, you're going to then use these numbers to create your test intervals, and that is where we were setting up our number line with our critical numbers. Then you determine the sign of your derivative at one test interval or one test value in each of the intervals. So you would go through and decide positive, negative, positive by plugging into your derivative. And then from there, if you got a positive sign, you would know that your function was increasing on that interval, and a negative sign would tell you that your function was decreasing on that interval. That's a quick recap of what we did yesterday. So we want to start with a quick warm-up problem where we have a function f of x equals 2x cubed minus 3x squared minus 36x plus 14, and we want to go ahead and do just that. We want to find any intervals where our function is increasing or decreasing. So in order to find our critical numbers, remember we first have to actually find f prime of x, or our derivative. So looking at this function f of x, using our power rule f prime of x, we would get 6x squared minus 6x minus 36. From here, we want to locate any of those critical numbers. So we're going to find where our derivative is equal to 0. When we set this equal to 0, I'm going to go ahead and factor out that GCF of 6. So we have 6 on the outside. X squared minus x minus 6 equals 0, which factors of negative 6 that add up to negative 1 are going to be negative 3 and positive 2, so x minus 3 and x plus 2. So we get critical numbers of x equals 3 and x equals negative 2. Scanning our equation, we don't have any vertical asymptotes, vertical tangents, or cusps. We don't have a denominator that's going to have a problem, so those are all the critical numbers that we have. Our final step was to test our intervals in f prime of x. This is where we set up that number line, plotting our negative 2 and our 3, and then plugging in one value in each test interval. So let's plug in something like, I don't know, a negative 5, a 0, and a positive 5. Yesterday I typically plugged into standard form. Today I'm going to try plugging in to factored form to see if that's a little bit easier to determine our sign. So let's look at f prime of negative 5. Plugging in where we factored would give us 6 times negative 5 minus 3 times negative 5 plus 2 would give us 6 times negative 8 times negative 3 would be a positive times a negative is going to give us a positive value. If we look at f prime, let's jump up here, I'm going to run out of room. F prime of 0, we would get 6 times 0 minus 3 times 0 plus 2 would give us 6 times negative 3 times positive 2 is a positive times a positive leaves us at a negative. And finally, f prime of positive 5 gives us 6 times 5 minus 3 times 5 plus 2 is 6 times 2 times 7, positive leaves us with a positive. So once we've identified those values of our derivative, the third and final step, or the final step, is going to be to determine the intervals of increasing and decreasing. So from here we know our function f of x is increasing on the intervals where we had a positive value. So on our two outside intervals, which would be from negative infinity to negative 2 and union from 3 to infinity, and our function f of x is decreasing in that middle interval there from -2 to 3. So as a quick recap, we used the first derivative to help us determine intervals of increasing and decreasing for our original function f of x. So today we're going to take what we learned yesterday and we're going to actually extend it from just increasing and decreasing to now talk about relative extrema, so a relative minimum or a relative maximum. To do that, we are going to look at what's called the first derivative test. And I'm just going to add on here for relative extrema. So it says, let C be a critical number, so those critical numbers that we just reminded ourselves of a function f that is continuous on an open interval I containing C. If f is differentiable on the interval except possibly at C, then f of C can be classified as follows, and then we have 3 scenarios. So for each of these, we're going to be considering all of the things that we did yesterday and that number line test that we did. So number 1 says if f prime of c, so if the sign of the derivative changes from negative to positive at c, then f, our function, has a relative minimum at the point c, f of c. So what that means is if we're doing the test like we did yesterday, and we set up our number line with our critical number in the middle, and when we test our value, on the left-hand side, we get a negative, and on the right-hand side, we get a positive, then what our function is doing is decreasing until that critical number, which I guess we're calling C, sorry about that, and then increasing after that, then that makes point C a relative minimum, or the point at C a relative minimum, because your graph is decreasing and then increasing. Similarly, in number 2, it says if f prime of c changes from positive to negative, so we have that same number line test. Here is our critical number c. When we test those values, we get a positive and then to negative. What's happening is our function is increasing and then our function is decreasing. So we're increasing and then decreasing, which makes that point at c, f of c, a relative maximum. So we're taking the steps we did yesterday and just extending them a little bit to identify relative extrema. And then finally, the third one just says if f prime of c is positive on both sides or negative on both sides, so that means something like this happens. You test and you get positive, positive, or negative, negative. Then looking at these 2 graph examples, it says f of c is neither a relative minimum or a maximum. You have something like what you see here, where you have that point as not relative extrema. So this is your first derivative test for relative extrema. We're going to be using this to extend what we did yesterday for just a couple of examples to identify a relative minimum or a relative maximum. Okay, so for our first example, the directions say find all the relative extrema of the function using the first derivative test, where our function is f of x equals 2x cubed minus 3x squared minus 36x plus 14. Hopefully you recognize this as the warm-up problem where we already did all of the work to identify the intervals of increasing and decreasing for this function. So bringing in that work, which looked like this, we already found our derivative f prime of x. We set that derivative equal to 0 to find our critical numbers since we didn't have any additional problems like a denominator or anything there. Then we set up our test intervals and we tested around them in f prime of x to determine our sign of our derivative, and we determined the intervals of increasing and decreasing. Extending that using the first derivative test, we want to identify that we were increasing and then decreasing. So at x equals -2, our derivative, f prime of x, changed from positive to negative, which means at x equals -2, we have a relative maximum. And then we were decreasing and changed to increasing. So the sign of our derivative changed from negative to positive at x equals 3, which makes that a relative minimum. However, we don't give points just as x equals. When we give our relative extrema, we want to give it as c f of c. So we have an additional step that we get to add to our process where we actually want to plug in our x values where we found relative extrema back into our original function. So we're going to use our original function f of x to find our ordered pairs. So we want to investigate f of -2, going back up to our original function. F of -2 would be 2 times -2 cubed minus 3 times -2 squared minus 36 times -2 plus 14. So we get f of -2 equals 58. And then also evaluating f of 3, our original function is 2 times 3 cubed minus 3 times 3 squared minus 36 times 3 plus 14, and we get f of 3 equals -67. So we can write our final answer, our relative extrema, as our function f of x has a relative maximum at the point -2, 58, and a relative minimum at the point 3, -67. So we are taking what we did yesterday, all of the stuff that we did in the warm-up, and just extending it to identify where the signs of our derivative is changing from positive to negative or negative to positive, and then finding that ordered pair of our relative extrema. Okay, so for our next problem, we're going to do this one all the way through, finding all of the relative extrema of the function using our first derivative test. So we're going to start just like we did yesterday. We need to find our derivative, our f prime of x. Using our power rule, f prime of x just equals 4x cubed minus 3x squared. Once we have our derivative, we are looking for our critical numbers, which we can do here by just setting this equal to 0. 4x cubed minus 3x squared equals 0. Taking out that GCF of x squared, we're left with 4x minus 3 equals 0, and we get two critical numbers. We get x equals 0 and x equals 3/4. Just like we did yesterday, we're going to test intervals in f prime of x. So we're going to set up our number line, identify our critical numbers as 0 and 3/4, and then we're going to test around them. So let's test values like -1, 1/2, and maybe 1. We're testing in our derivative. So let's look at f prime of -1. Plugging into our factored form, I get -1 squared times 4 times -1 minus 3. Whoops, that's too many parentheses. Gives us -1 squared is just 1. -4 minus 3 is -7. Positive times negative gives us a negative. Plugging in 1/2, f prime of 1/2 gives us 1/2 squared times 4 times 1/2 minus 3. 1/2 squared is 1/4. 4 times 1/2 is just 2, minus 3 is -1. Positive and negative give me that negative. And then finally, f prime of 1 would give us 1 squared times 4 times 1 minus 3. 1 squared is just 1, and 4 minus 3 is also 1. Positive and positive give us a positive. Now, yesterday we were identifying our intervals of increasing and decreasing. At this point, we're actually not going to list them out. What we want to look at is there a change in sign at our critical numbers? So what's happening is we would be decreasing on our first interval and decreasing again on our second interval. So at x equals 0, since we didn't have a change in sign, we do not have a relative extrema. But then we're increasing on our last interval. So at x equals 3/4, our derivative changed from negative to positive, which means we have a relative minimum because our function was decreasing and then changed to increasing. So the added step today is we're going to use our original function f of x to find our ordered pair. So we're going to plug in f of 3/4. So going back to our original function, we get 3/4 to the 4th minus 3/4 to the 3rd, and I'm going to reach for my calculator for this one. 3/4 to the 4th minus 3/4 to the 3rd, and we get a decimal equals negative 0.11. So we would say our function f of x has a relative minimum at the point 3/4, which I'm going to write as 0.75, negative 0.11. Last problem of the day, let's go ahead and find all of our relative extrema for the function f of x equals 2x minus 3x to the 2/3 power. Just like we have been for the past day or two, we're going to start by finding our derivative f prime of x. Using our power rule, the derivative of 2x is just 2 minus the derivative of 3x to the 2/3, bringing that 2/3 in front, 3's cancel, we're left with 2. X to the 1 less power, and 2/3 minus 3/3 would give us that negative 1/3. So I'm going to rewrite this as 2 minus 2 over x to the 1/3, and then just finding that common denominator, x to the 1/3 over x to the 1/3. I'm going to write my derivative f prime of x as 2x to the 1/3 minus 2 over x to the 1/3. Now from here, we want to find our critical numbers. Which remember happened where our derivative is equal to 0, so we can take that numerator, 2x to the 1/3 minus 2 equals 0. Factoring out that 2, we get x to the 1/3 minus 1 equals 0, so x to the 1/3 equals 1. So x just equals, cubing both sides, 1. Or also at those vertical asymptotes, vertical tangents, and cusps, which we would get from our denominator, equaling 0. So we would get x to the 1/3 equals 0, cubing both sides, x equals 0. The third step is to test our intervals in our derivative f prime of x. So setting up that number line, we have a critical number at 0 and a critical number at 1. Choosing values to plug in, let's plug in something like -1, 1/2, and maybe 2. We're plugging these into our derivative, so looking at f prime of -1, let's look at this as let's think of this derivative as being 2x to the 1/3 minus 1 over x to the 1/3. See if that's a little bit easier. So here we would get 2 times -1 to the 1/3 minus 1 over -1 to the 1/3. -1 to the 1/3, the third root of -1 is still going to be negative. Minus 1 is going to be negative. Times 2 is going to be a negative over a negative, which is going to give us a positive value. If we look at f prime of 1/2, we have 2 times 1/2 to the 1/3 power minus 1 over 1/2 to the 1/3 power. So if we look at what is the third root of 1/2, we get a decimal, minus 1 gives us a negative, times 2 is negative 0.4. So this is a negative value over the third root of 1/2 is going to be a positive value, which gives us a negative value in this interval. And then finally, f prime of 2 is equal to 2 times 2 to the 1/3 power minus 1 over 2 to the 1/3 power. 2 to the 1/3 power is positive, minus 1 is still positive, times 2 is still positive, over the third root of 2 is a positive number. Positive over a positive is a positive. That's my least favorite part. So we've identified the signs on each of those intervals. So now I want to go ahead and identify our relative extrema. So our function would be increasing, then decreasing, then increasing. So because we change signs at both critical numbers, both of them are going to be relative extrema. At x equals 0, we change from positive to negative. So we have a relative maximum. And at x equals 1, because we change from negative to positive, we have a relative minimum. And then we get that bonus added step where we get to use our original function f of x to find our ordered pairs. So we want to look at f of 0, plugging into our original function, we get 2 times 0 minus 3 times 0 to the 2/3 power, which just gives us 0. And looking at f of 1, we get 2 times 1 minus 3 times 1 to the 2/3 power, which gives us 2 minus 3, which is just negative 1. So we can say our function f of x has a relative maximum at the point 0, 0, and a relative minimum at the point 1, negative 1. Great job with these problems today. Homework 30 is the same section as homework 29 was. Now you just have numbers 23, 25, 27, 29, and then also numbers 33 and 35. If you have any additional questions, you can reach out to your teacher.